In a manner very similar to building with Lego blocks, new and unique materials and structures become accessible through the careful tuning of chemical and physical interactions, and then allowing them to run their course. Analytical methods primarily fall into two categories. On one hand are techniques that offer supreme levels of spatial resolution, capable of resolving single molecules and even single atoms. As one half of the technique I apply in my research, I want to highlight the scanning tunneling microscope, or STM. The STM enables the real space imaging of surfaces at the atomic level. An atomically sharp tip is brought close to a surface while a biased voltage is applied, leading to electron tunneling. This tunneling current is a function of the tip surface distance, applied voltage, and the local density of states. It is important to note that although STM images appear topographic in nature, the apparent heights are a consequence of the variations in the local density of states, which are a convolution of the electronic states of the tip, surface, and any adsorbed species. Additionally, conventional STM lacks chemical sensitivity, requiring a priori knowledge in order to identify atomic or molecular adsorbates. Vibrational spectroscopy is necessary to identify chemical species by their vibrational fingerprints. This can be addressed with inelastic electron tunneling spectroscopy, but this crucially requires UHV conditions and liquid helium temperatures. However, optical-based spectroscopies, such as Raman spectroscopy, can provide chemical information in nearly universal conditions. Raman spectroscopy relies upon the inelastic scattering of light by matter. Most commonly, Rayleigh scattering occurs, where the incident and emitted photon have the same energy. However, in a rare process, the emitted photon can have lower energy, as the molecule gains vibrational energy, which is known as Stokes Raman scattering. A Raman spectrum that results from Stokes Raman scattering can provide a highly sensitive vibrational fingerprint of a molecule's or material's structure. However, Raman scattering is a very weak process. Only about 1 in 10 million incident photons are scattered inelastically. In order to obtain a Raman spectrum of a molecular monolayer, it becomes necessary to use enhanced Raman spectroscopy. Under illumination, the electron density of a plasmonically active nanoparticle can couple with the electromagnetic radiation, resulting in the coherent oscillation of conduction electrons. The localized surface plasmon resonance generates highly confined enhancement fields, referred to as hotspots. This effect is the primary mechanism for surface-enhanced Raman spectroscopy, or TERS. Since countless hotspots occur within the nanoparticle arrays used for TERS, the spatial resolution of this technique is diffraction limited due to the use of lasers in the visible range. By using an STM tip made of a plasmonic metal, it becomes possible to confine the enhanced field at the atomic apex of the tip, making a single hotspot, and then use the STM to perform tip-enhanced Raman spectroscopy, or TERS. This method combines the spatial resolution of the SPM, chemical information from Raman spectroscopy, and single molecule sensitivity from TERS. These advantages have resulted in its implementation in studies in diverse conditions. Implementation of TERS in ultra-high vacuum can yield spectroscopic information with Angstrom scale resolution. Light becomes confined to a picocavity, leading to about 1 angstrom resolution and enhancement factors of up to 10 to the 12th and 10 to the 13th. This results in the ability to obtain full vibrational fingerprints for a few molecules, or even a single molecule adsorbed on a surface. My research relies upon an ultra-high vacuum, or UHV, custom-built variable temperature scanning probe microscope coupled with optics. This schematic illustrates the optics that allows to efficiently couple lasers of multiple wavelengths to the tip sample junction via a combination of optical fibers and flipping mirrors. Our excitation and collection lenses are located inside the chamber on the STM stage. Piezoelectric motors allow us to optimally and reliably focus these lenses for each sample and tip. The use of fiber optic coupling allows us to decouple the STM table from the spectrograph and larger lasers that are housed on the optical table. UHV STM TERS enables the study of subtle, local chemical effects at the Angstrom scale. This includes molecule-substrate interactions, intermolecular interactions, and even reactions on surfaces. Here, I would like to highlight work that I've led and contributed to during the course of my PhD studies. Boron subthiocyanine chloride, or sub-PC, is a unique member of the thiocyanine family composed of 3 isoindylyl lobes which form a 3-legged bowl structure with a central boron atom that is connected to a chlorine atom, forming a polar boron-chloride bond. On a silver 100 surface, STM imaging identified 2 possible binding configurations for sub-PC molecules. Molecules with a bright central protrusion could be identified as a chlorine-up binding configuration, while molecules that lacked a bright center correspond with a chlorine-down configuration. Sub-PC molecules of the same binding configuration were found to aggregate and form highly polarized molecular domains with large collective dipole moments. Using the spatial resolution of TERS, it was possible to capture vibrational fingerprints that correspond to each type of molecular island. As shown here, we found these vibrational fingerprints to be largely degenerate, suggesting a weak molecule-substrate interaction. By comparing these vibrational fingerprints with gas-phase time-dependent density functional theory, or DFT simulations, the molecule-substrate interaction was found to manifest primarily in the stretching mode of the axial boron-chloride bond of the sub-PC molecules. The observed vibrational mode exhibits a blue shift of 37 relative wave numbers compared to simulations. Although the structure of sub-PC is rigid and remains unchanged upon adsorption, it is possible for the conformation of a molecule to change significantly when it interacts with a surface. Polycyclic aromatic hydrocarbons, or PAHs, have generated significant interest following the discovery of methods to fabricate nanographene on surfaces. However, PAHs can exhibit non-planar flexibility due to rotation about sigma bonds, or even flexibility within the CC bonds that form their skeletal structure. This flexibility can result in unique binding conformations or orientations on surfaces. Subsequent reactions or thin film functionalities depend upon the reliable control of these factors at the single molecule level. We studied Rubrene, an organic semiconductor with an exceptionally high carrier mobility as a thin layer single crystal, on silver 100. Rubrene consists of a tetracene backbone with 2 phenyls on each side. STM imaging revealed the formation of 3 unique supramolecular assemblies, 2 types of molecular islands, as well as 2 molecule-wide molecular chains. By comparing TERS vibrational fingerprints with DFT simulations, we uncovered that these 3 self-assemblies were composed of 2 types of molecular binding conformations with Angstrom scale resolution. Rubrene was found to adsorb either with a tetracene backbone perpendicular to the substrate or with a flat orientation where the tetracene backbone lies parallel with the surface. TERS revealed unique vibrational fingerprints for each conformation. Our Rubrene molecule was found to adopt a flat orientation when surrounded within a molecular island, while a decrease in the density of intermolecular interactions results in a vertical orientation. The spatial resolution of TERS was tested by acquiring sequential spectra across the boundary of a molecular island as shown here, where the 1311 wave number vibrational mode corresponds with a perpendicular orientation, resulting in Angstrom scale resolution of the different binding orientations. Moving beyond molecule-substrate and intermolecular interactions, we have used UHV STM TERS to study surface reactions. Due to its ability to distinguish chemical identity, even in the case of adjacent regioisomers, as we showed in this study of positional isomers of porphodilactone molecules on silver 100, it was possible to identify cis and trans regioisomers with 8 Angstrom resolution, making UHV STM TERS an ideal method to consider the effects of local chemical environments on surface-bound reactions. Aromatic precursor molecules containing aryl halides can undergo dehalogenative coupling reactions via thermal activation on a metal substrate, yielding atomically precise nanocarbon structures. Although a leaving group, the halogen atoms can remain adsorbed on the surface in some cases. This can result in highly localized chemical environments where the halogen atoms can stabilize reaction intermediates and therefore enable the on-surface synthesis of unique nanostructures. We studied the Ullmann-like coupling reaction of 3,6-dibromophenanthroquinone, or DBPQ, on a gold 100 surface. Following thermal annealing, the leaving bromine atoms were found to form self-assembled islands and modify the surface reconstruction. Cis dimers formed on the bare gold surface, while trans dimers were observed within bromine networks with total selectivity. With an increase in the annealing temperature, polymeric chains were observed propagating from the bromine networks, while the cis dimers were found to terminate at S-shaped tetramers due to steric hindrance, suggesting the potential to purposefully use adsorbed leaving groups as a tool to steer bottom-up fabrication methods. The previously mentioned studies only serve as a sample of the capabilities of UHV STM TERS and my work during my studies. More recently, I have expanded to new on-surface reactions, finding unique products resulting from coordination chemistry, as well as revealing the vibrational fingerprint of the products of an intramolecular reaction. To conclude, as a truly tandem technique, UHV STM TERS occupies a unique position among surface characterization methods. Simultaneous STM and TERS imaging provide real space localization of detailed vibrational fingerprints at the Angstrom scale, enabling the study of the effects of highly localized chemical environments on molecules, materials, and reactions.